All right, so this morning we're going to finish least squares and linear regression. So try to pack up everything and in this coming hour. And on Wednesday, so we'll have the first lab, which will be on least squares. And we'll do as well on the afternoon, we'll start we'll either start working on logistic regression or do a tutorial. We'll probably do a last tutorial on these squares for you to see what kind of exercises you have. Okay. So I understand that you don't have previous year's exams. Okay. So the idea would be that the tutorials are examples of the kind of exam questions you might have. Okay. So there might be some questions that are a bit unrelated, but I will flag you and tell you what are the kind of questions you might have at the exam. Okay, so in the last course, okay, so we looked at the fitting. So we've seen all the mechanism to do the estimation of the weights that allows you to fit your linear model. Okay, and we've seen that the model, that's important. Okay, so the model is linear in the features, but the features can be whatever you want. Okay, so that gives you way more expressivity than you think. So this was the example when you're trying to fit a polynomial of degree 2. And then we saw that you have two types of problems that are relevant to machine learning, which the first one is underfitting. So underfitting, your model is not rich enough to fit your data. Okay, so your data follows a different model really than what your model can express, and that means that there is no way that you can fit your data. And what I said that the best way, like a symptom of underfitting, is that the loss function. So here remember that the loss function is the mean square error. So the loss function is actually quite high. Okay, so regardless of how you try to fit your data, you cannot just quite get a good error. Okay, so that's a symptom for underfitting. All right. So the other aspect, other problem you can have is overfitting. And so overfitting is that you say, okay, so you realize you were underfitting, so you say, what I need to do is to rank up the model. And so here we have a polynomial of order 9, so we say, we'll be safe enough for that. And indeed, you're safe enough, but as you can see, so the model you have is this solid red line. And as you can see, okay, you fit your data amazingly well. In fact, the error here is very low. Okay, you'll be like, I'm doing a very good job. But obviously, this is not very good. And it's not very good because if you have new data coming in and your data is outside of the range of your training data, so say if you have a point here or even a point here, then obviously the error will be way off. And basically, it's no good. Like you have a very good model for your training data, but on any new data that comes in that is different, basically you're making an enormous error. Okay. So this is the second problem you have, overfitting, and the symptoms are exactly what I said. Okay, you're doing very well on your training sets, but as soon as you try to apply it on data you haven't seen, then it just seems to be very poor. Okay. By the way, here I use polynomial models, but you could have any kind of feature base, so you could have cosines and sine and so on. Okay, so in the slides I've used a polynomial model because it's a convenient one to write down, but the idea is the same for any kind of model or any kind of features you use. So these two problems are really at the heart of machine learning. Okay, and I'd say the problem with overfitting is that your model, if it's rich enough, you can pretty much fit anything. Okay, so you have a polynomial model, and with that you, with a polynomial, if you use Taylor expansion, okay, you remember that you can basically approximate any function with a polynomial basis, okay? So it makes sense, right? You know you can fit any data. So how do you do to combat, to fight overfitting, okay? And the best way, well, the first way you can do, okay, is like you say, right, my model is too rich, I'm just going to simplify a bit your model till I reach, if I reduce a bit the size, the degree of my polynomial, then at some point I'm going to be correct, okay? So that's the other, the idea here in our example. We had a polynomial of order 9, but the underlying model was of order 2. And that seems simple enough, but in practice it's very hard, okay? Because there's a simple fact, which is that if you give a polynomial of order 9, you can actually fit as well. If you give enough data, you actually fit a model of order 2 as well, okay? Because when you give enough freedom, actually you can fit correctly. So it's actually can be really hard in real life to know what order you're into, okay? So even so, okay, simplifying your model seems like a good idea. Sometimes it's not very easy to know where you're at and to know which is the order of your model. So the best way to approach it when you have overfitting is really to give more data, okay? So you're trying to give more training data. So you come back to the example here we had. What happened here, the reason why it was not very good is because we had only, like, I don't know, it was like 8 points or something like that, okay? So we have a very few number of points, and we're using a polynomial of order 9. So we know, you need at least 9 points or 10 points or something like that. But that's probably not even enough, okay? You probably need, hundreds of samples. And not only that, but you need them to be spread across the whole range of data you might have, okay? So if you want the distribution of your training set, the points you have, must kind of match the distribution of the data you're going to test, okay? So you want your training set to cover the whole range of data you might actually use against, okay? So that's the main thing, okay? If you have overfitting, the first course of action should be just use more data, okay? Just use more training, try to get to source more examples and use those, okay? The thing is, sometimes you might not have enough data, okay? And the answer to that is just go back and get more data, okay? I mean, I just can't emphasize that enough, and especially in deep learning, okay? Deep learning, 99% of the problem you have will be that you're overfitting, and the only thing you have to do is just to say, right, I only put 1,000 examples, images at the training set. That's not enough. I need to put 1 million, okay? I need maybe to put 10 million pictures, okay? And it's only when you put 10 million pictures, then you're able to converge, okay? So the same idea here. The amount of data you have is really important. It's just the more data you have, the better you do, okay? But obviously, maybe your model is very rich, and it's kind of hard to get data everywhere, okay? Then you have like billions and billions of data. So there's one mechanism that allows you to solve that problem of the lack of data you might have, and this is called regularization, okay? And once again, this is something you will see in most machine learning algorithms, and this is not just specific to least square. Okay, so I just briefly derive what we have, and this is called the Tikhonov regularization. Now, there's many ways of spelling Tikhonov. Okay, this is a Russian name, and This is just one of the many ones. So I just want to come back for a second on the loss function we had for least squares. Okay, so we had a function of a vector of weights, and we said that basically this was equals to design matrix times your vector of weights minus the vector of all the outcomes, and this was equal to this transpose this. Okay, so remember that's what we've seen before. So the Tikhonov regularization said that, okay, in some situation, basically we have many solutions for W. Okay, and what happened in overfitting is that actually we didn't have any constraints on your linear system. So we had our metrics, and the matrix universe. So remember we had x transpose x times W equals x transpose y. So these were the normal equations. And the issue we have basically is that this matrix here is close to singular. Okay, so the effect of overfitting is that this matrix here is not. You don't have enough data to actually have a good approximation of what this matrix should be, and this matrix is hard to invert. Okay, so. And singular means hard to invert. Okay? So that was kind of the issue we had, okay? So the way Tikhonov approached the problem was to say, what we need to do is to add some kind of penalty on the weights. We need to say, okay, when we try to invert this, basically there's too many options for W, okay? And so we need to constrain what the choice of W should be. So the way I approach it is just to add one little term, okay? So we said that on this side, the first part of the first term is the send, so that's your loss function you had before. And we're just going to add a little penalty term here, okay? So this guy, what it is just the norm of your weights, okay? So that's your new energy function or new loss function, okay? So give it a prime. So what is the effect of that, okay? So we say we have one term in the loss function that says we want the data to fit. So we want the prediction, so that's your prediction, okay? And that's the actual outcome. So that was, we want the prediction to match the outcome, but as well, we want W to be small, okay? And that might seem a bit strange. Why do you want W to be small? It's slightly arbitrary, but the point is, if you do least square, okay, what is more likely? Is it more likely that, I'll just show this example here. Is it more likely that the curve you want to fit is this one, okay, with numbers that are reasonably small, or to have something like that? Okay? So given the choice between the two, you probably want to pick up the coefficients to be small, okay? Because powers of 10 to the power of 10 is not something you like to manipulate, okay? So it's a reasonable point, okay? So you just say, all things considered, if I don't know anything more about the weights, I want the weights to be quite small, okay? And another way of looking why this is interesting is because of this extrapolation problem, okay? So you have your let's say you have your data, and you want to fit a line. Now, if the weights are very large, okay, so if the weights are very large, then in 2D at least, your slope is going to be very high, okay? That's what it says. And that means that if you're given a new point, okay, a new sample here, then the new estimate is going to be very, very, very high, okay? Makes sense, because you're going to have something like, say, this, but if your slope is very high, then the outcome will be extremely high, even higher, okay? And that's kind of unlikely to be, outside the range of your domain, okay? So all things considered, it's more likely to have something that will be, a small slope, okay? So it means like when you extrapolate, when you have a point which is actually far away from your original domain, then the new estimate is not crazy, it's still something reasonable. Okay, so that's about the idea behind it, okay? And we're just going to quickly derive what the implication of this, okay? So we're going to use here the same mechanism as a derivation that we had for least squares. Okay, so basically we said that the gradient of this new loss function must be 0 for all the weights. So remember, this is a vector of zeros. Okay, so the gradient of this expression here, if you want, that's the gradient of the original loss function plus the gradient of this extra term, which is called the regularization term. Okay, and so this is the gradient of the original loss function, and we know from the previous course, lecture, that this will be something like this. So x transpose xw minus this, and so this is from the previous class. And then we have this term here. And if you come back to the table of, I gave you a list, remember, in the first lecture of examples of how you do the gradient of the matrix notations. Well, basically, alpha is a constant gain, so that goes unchanged. And then you have the gradient of W transpose W, which is basically, sorry, this is twice 2, which is 2 times W. Okay? And then I can reorganize all that. Okay, so I have a term here, which is x transpose x, W minus 2x transpose y plus 2 alpha W. So I'm going to combine the terms in the weights, and I have x transpose x plus alpha times the identity matrix times W minus, I'm sorry. Okay, so there's a little trick here. So I had here 2 alpha times W, okay? And this is a scalar, okay? But another way of writing the scalar is to say it's the identity matrix times W, okay? So the identity matrix, if you've forgotten what it is, it's just ones on the diagonal and zeros elsewhere. And when you multiply the identity matrix by W, you just get W. Okay? It's just the matrix that does nothing. Okay? So it's like the equivalent of 1, if you want. Okay, so I just remove the 2's and put everything in the correct place, and basically you get an alternative expression for your normal equations. Which is this one here, okay? So you still have your X transpose X matrix with O, okay? So this is what a P by P matrix. And you have alpha times the identity matrix and the rest here, which is the same. So really what's happening here, okay, it's quite simple. To get regularization, you basically have the same equation, and the only difference that will happen is that you look at this X transpose X matrix, and you're going to add a small number to the diagonal elements. Okay, so it's a classic trick you do in physics or in maths. If you have a problem to invert this matrix, basically we say, okay, we're going to add on all the elements of the diagonal, we're going to add a little something. Okay, and this one is alpha. And by doing that, basically I'm going to bias the W's to be a bit smaller. Okay? So that's regularization, okay? And it's quite simple. I mean, it's designed to be still linear. You don't change your framework. You don't have to involve new maths, okay? It's still the same kind of equations. Everything is still simple and still the same framework. And that's the reason why we use that type of regularization. So as I said, you want to do that for the effect it has. It will help you with the inversion of that matrix, and it will create a little bias on W to make it smaller. And so they're very useful for overfitting because by adding this little bias, you make sure that your data doesn't tell you that the gain is massive or this matrix is very close to being 0 or something like that. Okay, so you kind of limit the scale of what the prediction should be. Okay, you don't say the prediction, whatever happens, I don't want the prediction to be mad and to go at very high values. So as you can see, regularization is quite it's simple enough in that case. Okay. And that's because we used just the square here. You have different types of regularization. Sometimes you have what's called the L1 regularization, in which case you're going to add the L1 norm, which is basically the absolute value, the sum of the absolute values of W's. Okay. This is maybe more interesting than the L2, but it's much harder mathematically to solve. Okay, so we're not going to go there and just say it exists. And sometimes you see people talk about L1 regularization, and that's what they mean. Just mean that instead of taking the square of the sum of the square of the values, they take the sum of the absolute values. Okay? So the way I see regularization, it's a bit like a necessary evil, okay? You'd love not, like, you know when you add regularization, you're going to bias your data. So if your data is correct, then when you add regularization, chances are you're going to make it incorrect, okay? But usually you have to use it somehow because however the amount of data you put in, most likely you won't cover the whole possible range of all your data. So you always need to account for the fact that you might be slightly off, and maybe if you bring a new data that is very far away from your training set, then it will all go banana, and therefore you want a bit of regularization. Okay, so that's it for regularization. I just wanted to finish this part here with just introducing the concept of maximum likelihood. Okay, so very early on, actually, even from, that's how Gauss was famous, okay? That Gauss made the connection between probabilities and least squares. So if you want, the founding father of statistics in that sense was Gauss, and when he made the link between least squares and distribution. And I'm just going to go through that because very similar reasoning will happen for logistic regression. So this is the model we have, okay? So we have our linear model and matrix notation, and we have this term epsilon here, okay? And what Gauss has done, okay, he said, right, what if we try to give that a probabilistic view and try to see what kind of error has epsilon, okay? And he said that basically we're going to assume that epsilon follows what's called a Gaussian distribution, which basically, if you plot the histogram of epsilon, so this is epsilon here, okay? And this is kind of the histogram of the frequencies of the values of epsilon, okay? So it's mainly centered in 0 and then kind of tails off at the end, following the normal distribution. I think in theory you've all seen that. Has anyone not seen the Gaussian distribution? Everybody has seen it? Yes? No? Okay. It should have happened. So anyway, so that's how it works, okay? So so let's see if we do this, what the consequence. So I'm trying to link now the least square estimate to this probabilistic view, okay? So if you look at the likelihood, of, for a particular sample, okay? So we remember we have this model. Sorry. So I'll just write it again. Okay, so that's your linear model for a particular sample. And so I can write that epsilon is the outcome minus the predicted value. And if you look at what is the likelihood of epsilon, well, the likelihood is the probability of that epsilon is this particular value, okay? Given given that we know what the weights coefficients are, and given the fact that we know what the feature vector is, and we know the outcome. Okay. So here we're just checking that. Okay, we have all the information available. We have the weights, the outcome, and the features, and we have an error that we can derive, and we just look at the probability of this error according to our model. Okay? And that is basically exactly what was given by the equation before. Okay, so the model we have for epsilon. Okay, that's quite simple. So we have basically we say epsilon has to follow a Gaussian distribution, and therefore the probability that epsilon, if this particular value, given the fact we assume we know them, is just given by the distribution we submitted. So that's for one sample. And now we're going to assume that the error is independent on each of the observations. Okay, so we're going to assume that what we observe on a particular, on the east, on the observation I is the same, that is independent of what we observe on observation I plus 1 and so on. Okay? So if we do that assumption that the the error is independently distributed, so then what we have is the likelihood for all the errors, and so we have the overall likelihood is simply the product over all my observations of that guy. And we have here a product of exponentials, so it's we can say it's a sum of the exponential of the sum. Okay? And here we see inside that term, this is our least square loss function. Okay? This is exactly this. So what Gauss has showed, okay, is that if you assume that it's independently distributed and that if your error follows a Gaussian distribution, then the likelihood of your error is actually related directly to your least square error, or to your squared error, sum of squared error. And therefore, if you try to find W hat that basically minimizes the likelihood, so that's called the maximum likelihood. Okay, so you're trying to find W that maximizes the likelihood, so the most likely W, if you want, actually corresponds to, is equivalent to taking W hat, which is the minimum of this square. Okay? So given the right set of assumptions about your error, then it is equivalent to talk about maximum likelihood than it is to talk about minimum square. So the least square estimate is actually the maximum likelihood estimate. They're both the same. Are you okay? Yes, sir.
Can you spell that out for the class? Why is it making P of epsilon big means making that thing small? What's the key?
So, yeah, so the key reason why this is happening so you have basically the likelihood which is proportional, because that term here doesn't really matter, doesn't change anything, to exponential minus your energy, your loss function here.
The point is that thing is always positive, right? So minus is always negative. So to make that guy big, that
yeah.
positive guys.
Mm-hmm. So this guy is always positive, and therefore, you can apply the log, okay? So if you apply the log, so the log is a convex function, so it doesn't change the order in which you do things. So if you take the log of your likelihood, that's equal to plus some constant here. And then if you take the negative log of this, so k, the constant k doesn't matter, so the constant k comes from this coefficient here. And so we have the direct relationship here between the least square and the negative log likelihood. And because logarithm is convex, we take, so that doesn't change the order, so the maximum of this is still the maximum of this, okay? So that doesn't change the what is the maximum. And we apply negative, so now the maximum becomes the minimum. So the minimum of this guy corresponds to the maximum of that guy. Okay? So therefore, the minimum of this guy corresponds to the maximum of this guy here. Okay? So the key here that when you take the logarithm of your likelihood, you don't change the order. Okay? So the minimum of that function for W is still the minimum of that function for W. Okay? Going from here to here doesn't change where the minimum is. Okay, so that was it for it kind of finishes all the things you really have to know about this square. And the last point I wanted to make was, it's in the slides somewhere, it's some just historical notes, okay? They're not complete. And least square is actually a very interesting history, and I really highly encourage you to just go to Wikipedia and see what's going on there. There's a very nice discovery priority dispute on the discovery of least squares. So a number of people have independently looked at the problem. I mean, it's such an important problem in maths that it's not just like one person discovered it, it's a range of people. But basically, the first person that really published the least square is Adrien-Marie Legendre in 1805. And what he did is he wrote a little appendix to a paper he was doing about predicting the movement of celestial bodies. So he's looking at comets and other bodies and trying to predict where they will be in space. And so they had a rather complicated system to model where it should be, but basically they had to deal with the fact that they only had very few observations and they still had to predict what the actual parameters of these models would be. And so basically, at that point, he discovered that, well, we try to minimize the square of the error and so on, and that's what he called it. So least square is actually just a translation from the French moindre carré. Okay, so that's where it comes from. But then came along Gauss, and Gauss said, well, actually, I had done that before, but I just didn't publish it. And if you want my advice on that, if you don't publish something, then it's kind of hard to have any claim on having discovered it. But the story goes that, Gauss was so important and so clever that people say, well, if he says so, then probably it's true. And so now a lot of people would say, actually, he discovered this square and he's the inventor of it. But really, when you look at the history, the first paper was from Legendre. But what Gauss did, and that nobody else did, was to actually connect least square to the maximum likelihood. And that was a big deal because that kind of opened up a lot of the statistic involved in that. Okay? But these two people are not the only people involved. There's a number of independent discoveries around the same time. And it's quite fascinating because really the beginning of statistics. The last question is, why do we call that regression? What is regressing? Okay? And so regression is kind of a misnomer because actually it starts from a fallacy. Okay? So, and it's an interesting story. It's slightly outside the scope of this course, but it has to do with correlation. And I suppose it's a small point of warning, okay, for you. So what Galton was doing, so it started with Francis Galton in 1886, and he was basically looking at the evolution of heights in people. And so in the x-axis here, what you would have is the heights of the parents, and the y-axis would be the heights of the offsprings. And you can see it's a nice point cloud, and sure enough, you really want to have a line that goes through here. That's really your estimate for how a relationship between the heights of the parents with the heights of the offspring. And sure enough, he did that. So you're kind of expecting something like that. Okay, you're kind of expecting to fit a line here, the green line. But sure enough, you don't get that. What you get is this red line here, okay? And the red line basically means that if you have a value that is at the extreme, okay? So if the parent is very short or the parent is very tall, then most likely what is happening that your offspring will be, so if you're very short, then your offspring is more likely to be a bit taller, okay? And if you're very tall, then your offspring is more likely to be a bit shorter, okay? And that's kind of hence the word regression, okay? So, the things kind of regress, the population regress in size. So it's really to do with the extremes, okay? So at the extremes of your spectrum, you kind of expected that, if the input is extreme, then it's expected that the outcome is actually less extreme. And this is something that happens quite a lot, okay? So there's been a number of studies, say, I think it was Israeli jet fighters, pilots, and they were measuring their ability to do figures. They were doing acrobatics with planes. And basically, they would say, right, if a fighter is performing very poorly in one day, then the next day is more likely to actually perform better. Okay? Similarly, if a fighter is performing very good one day, then the next day is likely to perform less. We see that as well with drugs, okay? So kind of linked to the placebo effect. If you take a population of people and you look at their heart condition, and you say, okay, somebody has a very poor heart condition, okay? So we give a drug, and the next thing we know that he's doing better, okay? And you're like, oh, hooray, okay, we're doing, it's amazing. But actually, the drug doesn't do anything, okay? And what happened here is like, quite simply, in all these cases, there is some random variation. So on the day you picked up, it was just a bad day for that person, okay? Maybe the guy was drinking on the day before and therefore had a very bad heart condition on the day of the test. But the next day, he was sober and, of course, his heart was doing a bit better, okay? So, with the jet fighter, these people are, they're all very good, just had a bad day, and most likely the day after, the person was doing better. So, it's a known fallacy, okay, that you have to be careful with the extreme values and tend to, what you do on one instance doesn't happen in the next instance. And in the slides, I've written a little explanation of what this is happening. But basically, what you have to be careful of, okay, is the following. What we have here is like we have an underlying model which said that if you want the height gene, okay, I call it gene, it's probably very poor representation of what's going on, but the model is like the real height of the parents, the offspring, is a linear combination of something to do with the gene of the height gene of the parents, okay? So the offspring and the parents, okay? So V is the offspring and U is the parents. And that's indeed probably a linear model or something like that. But what happens, like, because of multiple reasons, you have noise that happens, okay? And the way we model noise, and this is very important, okay, was to add a noise on the outcome, okay? So remember, what we had in least square is this, okay? So we've added noise, but basically we've added noise to the outcome. Okay, we say the noise only relates to what's happening in the outcome. But it's really often that you have a noise in the features as well. Okay, so your input might just be a bit random as well. In which case, what happens here is that your weight your coefficient here, okay, so that's your weight, is multiplied against this input noise. Okay. And that is a totally different model from what we have, okay? Our assumption is that we have a model that linearly combines the features and adds some noise. And the noise is only in this part, in this epsilon here, okay? But what happens when you have noisy features is that the noise correlates with your weights, okay? So your weights have an impact. And if you want, the effect of that noise is that the best case for you is to reduce this W1, okay? Because if you set W1 to 0, then it totally cancels off the noise component you have in the feature. So it's written in the slides, but basically the effect of having noisy features is that the estimates, when you do least square estimates, you will tend to shrink this gain value here. Okay? This W1 will shrink in value. Okay? And so you will bias your estimates. Okay? And this is what happens here. Okay? So you're basically, if you just model what the noise happens, you have something very similar to the Tikhonov regularization. Okay? You have an extra term here in your X transpose X matrix, which has something to do with the covariance of the variance of your nodes. So this is what happens here, okay? You were supposed to have this green line, but because the noise kind of correlated, kind of mixed in with your weights, your estimate has to take a very conservative view on it and basically shrinks its value towards 0, biased towards 0, and so therefore the slope gets a bit dampened, okay? So you have a softer slope. Something to keep in mind, because usually when you use least square, and even when you use deep learning and so on, what will happen is you don't think too much that your data is noisy, or data is correlated with your output and so on. So usually that actually happens in real world, but there's nothing you can do too much about it. Okay, that's it for least squares. Thank you very much.